In our discussion of one-dimensional motion, we use the concept of vectors only to a limited extent. In our further study of motion, manipulating vector quantities will become increasingly important. So we know each of the physical quantities we will encounter in the further studies of physics will be categorized either a vector quantity or a scalar quantity. Vector has both direction and magnitude, magnitude meaning size. A scalar can be completely specified by its magnitude with appropriate units, and it has no direction. As we discussed earlier, displacement, delta x or delta y, are examples of a vector quantity. Velocity is another vector quantity, and acceleration is another vector quantity. Well, if a temperature of an object is -5 degrees Celsius, that information completely specifies the temperature of the object, not the direction it is required. So temperature, which sometimes we denote with the capital letter T, is a scalar quantity. Another scalar quantity will be a mass, which doesn't have a direction, and so on. Scalar quantities can be manipulated with the rules of ordinary arithmetics. Vector can also be added and subtracted from each other and multiplied, but there are a number of important differences, as I'm going to show. Let's say you have two vectors, vector A and a little arrow on the top, and vector B. So we say two vectors A and B are equal if they have the same magnitude and the same direction. So let's suppose vector A has a certain length or certain magnitude, and this is my vector A, and that would be equal to vector B if vector B has the same size and the same direction. So let me draw another vector, let's say vector C, which has, let's say, the same magnitude but a different direction. If you measure with the ruler, let's say both of them are 2 inches long, all of them are 2 inches long, but the direction of C is different from direction of A and B. So therefore, vector C is not equal to vector B, A, and is not equal to vector B. So this equality of two vectors having the same direction and the same magnitude allows us to translate a vector parallel to itself in a diagram without affecting the vector. In fact, for most purposes, any vector can be moved parallel to itself without being affected. So you can take, let's say, vector A and move from its place to somewhere here. As long as it's parallel and it has the same magnitude, this vector is remaining the same. Now let's talk about adding vectors. When two or more vectors are added, they must all have the same units. For example, it doesn't make sense to add a velocity vector carrying units of meters per second to a displacement vector carrying units of meter. Scalars obey the same rule. It would be similar, meaningless to add temperatures to volumes or masses to time intervals. Let's start with addition, geometrical addition of two vectors. The simplest situation occurs when the vectors point along the same direction, that is, when they are collinear. Suppose there is a car first moves along a straight line with a displacement vector A equals 275 meters due east. Then the car moves again in the same direction with a displacement B equals 125 meters, same direction, due east. So first let's point our starting point where the car starts, and then let's draw vector A. So the displacement A, let's say this is our vector, goes to the east, and then this is vector A. And then vector E, which is almost about a little bit less than the half of vector A, continues on. That's a vector B here. And that's the finish point at the end. So here's the finish. These two vectors add to give the total displacement vector, which is from the start to the end. And we call it R, vector R. The symbol R is used because the total vector is often called resultant vector. So when you want to add two vectors, you want the tail of the second vector located at the head of the first arrow. So if you have a vector like this is the tail, and here you have the head of the vector. So the tail of the vector B is just attached to the head of the vector A. So sometimes this method of adding two vectors, it's called head to tail method. So now if you want to write down mathematically this addition, you would say resultant vector equals vector A plus vector B equals 275 centimeters. Watch out, because it's a vector, you have to put the direction to due east plus 125 meters due east. So our resultant equals 400 meters due east. Now, what if the car moved due west after the 275 meters due east, meaning vector B is directed due west? Let me draw the situation for you. First, we place vector A, that is 275 centimeters. Why did I write centimeters? It has to be meters. Meters due east. So this is my vector A, and now now the car moves 125 meters due north. So which means if I do head to tail, I'm going to put the vector B head on the head of the vector A, the tail of vector B, and it's going due west. So this would be my vector B, and here we have the final point, finish. Okay. Now, since we're talking about displacement, the car displaced itself from the starting point to the final point. So we start, if you want to add this vector A to vector B, you start from the starting point and then you end at the finish. So this green one would be the resultant vector. Again, let's remember that the vectors to be added are arranged in a tail to head or head to tail fashion, and the resultant vector points from tail of the first to the head of the last vector, or from the beginning from the start point to the end point. So if we want to write this in mathematically and find the direction of the resultant vector and the magnitude, so here's what we do. So we're going to write resultant vector again equals vector A plus vector B. But first, we need to find the magnitude. So if you simply add 275 to 125, this will not be correct. It will not carry the direction of the vectors in it. So instead, we take advantage of the fact that this triangle we have is a right triangle. So pretty much we have this is a 90 degrees. And so we could use Pythagorean Theorem. Let's just make a quick recall of Pythagorean Theorem. I'm sure you know this, but real quick, and it's about the right triangles. So if you have a right triangle and you have A, B, the sides, and the hypotenuse to be C, then according to Pythagorean Theorem, A squared plus B squared equals C squared. So we're going to use that. In our situation, R is the hypotenuse, A and B are the sides of the triangle. So then I can write, to find the magnitude, I could write R squared equals A squared plus B squared. As you noticed, I don't put the little arrows on the top of the R, A, and B, just because I am dealing with the magnitude here, okay? So from here, I could say, take a square root from both sides. I will say R equals A squared plus B squared under the square root. Now I can plug in the numbers. That is a 275 meters squared plus 125 meters squared. Punch this into a calculator, we will get 302 meters. Now, the direction for the resultant vector is actually not very certain, east, north, or south, or west, or whatever. But there's an interesting thing here, that is this angle that could specify which direction our vector is pointing at. So to find the direction, we need to make a quick recall on trigonometric functions. Trigonometry is a very important branch in mathematics, but we're going to use only 3 trigonometric functions in this course, and I believe this is the furthest mathematics we will incorporate in our course. So I'm gonna remind you the definitions of 3 trigonometric functions. So and that is also about the right triangle. Let's say you have a triangle of that has a hypotenuse h. Here's a right triangle, and then we have an angle theta right here. So the side that is attached, that makes the angle theta with the hypotenuse, we call it adjacent side, and the side that is opposite to the angle, we're just going to call it opposite. Okay, so functions. The first one is the sine, function of sine. Sine theta equals opposite over hypotenuse. So opposite side over hypotenuse. Let me call this side as HO and the adjacent side HA. Like a subscript stands for H opposite and H adjacent. So I can rewrite sine theta equals H opposite over H adjacent. I'm sorry, or just simply H, hypotenuse. Okay, the next function is the cosine theta, which is adjacent side over hypotenuse. Adjacent over hypotenuse, which is HA over H. Finally, the last one is a tangent theta, which equals opposite side over adjacent side. That is HO over HA. So again, HO, HA, and HO and HA are corresponding to the length of a side opposite to the angle theta. HA is length of the side adjacent to the angle theta, and the length of hypotenuse of the right triangle is just denoted as an H. Now, using these trigonometric functions, we can find the direction of our resultant vector. So as you can see, we know the magnitude of vector A and magnitude of vector B. So and if you want to find the angle theta, so the magnitude of vector B would be your H opposite, and magnitude of vector A would be your H adjacent, and the R is your H, just the hypotenuse. We're not interested in that because we already have HO and HA. So opposite side and adjacent side are present in the function of tangent, so that I can write tangent theta. Tangent theta equals H opposite over HA, or B, the magnitude of vector B over A. Now, to find the value of theta, we have to do the inverse operation. So, which is inverse of tangent. So I'm going to write theta equals tangent inverse B over A, which equals tangent inverse 125 meters over 275 meters, and that is 24.4 degrees. Thus, I can say that resultant displacement of the car has a magnitude, so let me write it down, resultant vector. Now I put the vector sign because I'm going to give the direction as well, equals 302 meters at 24.4 degrees north of east. So what does it mean? North of east, you start from east and then you move to the north. So let's say this is north. Oh, I'm sorry, east. East. So you're moving to the north by 24.4 degrees. This is 24.4 degrees. So north is here. Okay. Now, what if the two vectors to be added are not perpendicular to each other? Let's say vector A is still going do is 275 meters, but vector B is 125 meters in direction of 55 degrees north of west. Let's draw the situation again. So we have vector A that is going due, this is the starting point, and it's going due east. Vector A here, 275, and then we want to draw vector B 125 degrees north of west. So if this is my west on the left and I have north on the top, south on the bottom, if you want to draw north of west, you start from the west and you go towards the north. Start from west and go to north. Okay, so I am going to start from west, measure 55 degrees towards the north, and then put the head to tail, and then draw 125 meter worth vector. So this would be my vector B. Here's a 55 degrees. Then the resultant here will be from starting point to the ending point. So end or finish and start. Well, now you don't have a right triangle. Therefore, the Pythagorean theorem and trigonometric functions are not valid. Well, in this case, we use a graphical method of adding. Which means all I need to do, use a ruler and measure the resultant vector R, and use a protractor to measure this angle. Okay, so most probably you would find certain values that I have no means to measure that on my screen. This method might not be very practical at this point, so there is another method is called the algebraic method, or sometimes it's known as the component method of the vectors. Let's discuss the components of the vectors in a little bit. I want to discuss how to subtract vectors from each other as well. The subtraction of one vector from another is carried out in a way that depends on the fact on a fact of multiplying a vector by -1. So what is the fact? When a vector is multiplied by -1, the magnitude of the vector remains the same, but the direction of the vector is reversed. For example, if you have a vector A and you multiply this by -1, then you end up getting -a vector, which has the same magnitude but the opposite direction. Well, let's draw this. So here's our vector A, and our negative vector A would be same magnitude but opposite direction. In practice, vector subtraction is carried out exactly like vector addition, except that one of the vectors added is multiplied by a scalar of factor of -1. To see why, let's look at the vectors A and B. Here's my vector A, and then let's put our vector b on the side, on the head. Let's make a little bit larger. We don't want equal vectors. This is my vector b right here, and I want to add them up. Then my resultant vector would be from the beginning to the end. So this would be vector a plus vector b. Now let's say I want to subtract vector b from vector a. So subtract, and what I would get, I can rewrite this as vector a plus negative vector b. Okay, so and then all I need to do to flip the direction of vector b and then do simple addition. Well, let's draw this picture now. So my vector a is right here. And then vector b, if I may draw negative vector b here for the comparison, and then move that to where my vector, I need to make sure that this is parallel, and it's hard to draw. Okay, so wiggly line. This is negative b. But these two vectors are not head to tail. So what I'm going to do, I'm going to move vector b and put the tail of vector b on the head of vector a. So let me use a different color here for vector b. Okay, so remember the property, I can move the vector in any direction I want to. So then I don't need this one because I moved it. Now my resultant vector would be from the beginning to the end. So this would be vector a minus vector b, which is vector a plus negative vector b. I will discuss the components of the vector in a separate video. Thank you for watching, and stay tuned for another one to come.